Hello friends, welcome to follow up. In this video, let's look at problem 142, linked list cycle 2. This is a continuation for today's daily challenge problem, that is linked list cycle 1. So here we're going to explain how to do this problem in a logically correct or rigorous fashion. Actually, I saw a number of solutions to this problem. So they basically touches the core of the solution or the logic, but not to a very sufficient extent. So in this video, we try to bring this gap. So here we have a linked list given a head. So we want to find the node where the cycle begins. And if there's no cycle, we are going to return null. So from the previous problem, we know we can use fast slow pointers to get or to check if there's a cycle or not. That's actually rather simple. But this problem actually is strengthened. So basically, we not only want to detect if there's a cycle or not, and also we want to check the entry point if there were a cycle, right? That's the main problem. So here in example 1 and example 2, there are indeed cycles. And in the first example, so the node at this one, that's 2, is the entry point. And here 1 is at the entry point, right? We want to identify this list node. So here we want to use an example to demonstrate this procedure. So if you look at this linked list here, I draw. So here actually 6 is the entry point or node for in this example. So the distance to entry is 6. So I call this distance to the entry point as 6 because you need, if you move one step further, so there will be 6 steps needed to arrive this entry point, right? So here the slow pointer first points to 0, same as the fast, and then it will need 6 steps to arrive here, right? So but the fast pointer moves 6 steps, so its moving distance is actually 12, right? So that's the difference. So we can actually examine where the two pointers meet. So at after 6 steps, so the slower pointer arrives at 6, and then the fast pointer actually travels a distance 12. So 12 corresponding to, so this 9, 6 corresponding to 10, 7 corresponding to 11, and 8 corresponding to 12. So the fast pointer actually is at 12, right? So in other words, 8. So then move forward. The slow pointer will be at 7, and then the fast pointer will be at 6, right? 6 corresponding to 14, right, in distance. And then we move the slower pointer again to arrive at 8 here. And then the fast pointer will travel a distance 16, corresponding to 8 again. So this is where they meet. They meet here, right? So in other words, when the slower pointer moves 2 steps in the circle, so once the slower one enters the circle and move 2 steps, then they meet, right? So here is the sentence. So 8 is the meeting point, and from 6 to 8, slower pointer moves this number of steps, that is 2, right? So we will call this n slow or n slow in cycle for preciseness. So in this one, the distance, the fast distance minus the slower distance is 8, right? So so because we traveled in total steps, and the slower travels 8 steps, and the fast travels 16 steps. So 16 minus 8 actually equals 8. So here 8 is nothing but 2 times the cycle length. So the cycle length here is 4, because it needs a long time to enter this cycle or arrive at this entry point. But the fast pointer have already arrived, so he began to cycle here, right? So that's the main logic. If you have a larger key, right, then the fast pointer will cycle more rounds around this cycle here. That's the main digest point. So here we have a 2. 2 is a multiple. So basically, k plus n slow or n slow in cycle is the number of steps the slower pointer travels. So if you multiply by 2, this is nothing but the distance traveled by the fast pointer. So it's actually equals to k plus slow. This is the number of steps or the distance the slower pointer travels. So the reason they meet is that the fast pointer travels more distance in the sense that a number of more cycles, right? That is m times the cycle length. So this m actually is at least 1 because the faster pointer travels faster than the slower ones. So it travels at least 1 cycle length long in distance, right? That's why we have m. So this m greater than or equal to 1 actually is very crucial for the genuine logic. So here we have 2k in the left side, and we have 1k in the right. So then we cancel 1, we have a k in the left. So here we have 2 n slows in the left, and in the right we have n slows. So we cancel 2, so we get negative n slow in the right. And then we have m times the cycle length. So notice that m is greater than or equal to 1. So we can always write it like this. K equals the cycle length. We pick 1 cycle length from the m, then use it minus the n slow. So this, because this distance and this distance is the n step. So if we use n cycle minus n slow, this means this part, right? So in this specific example is also 2. So this is the cycle length minus n slow plus m minus 1 times n cycle length. So if m equals 1, it means that the k number of steps is exactly equals to cycle length minus the n slow. So I guess it might be the case in example 1, but we can analyze that later. So basically, if when they meet, so the slow actually will pointing 8, and then if we use a reference starting from the beginning, and then we continue. So see, we move 2 steps, so the reference will arrive at 2, right? Reference and 2, and then the slow will arrive at the entry point 6, but they do not meet. And then we travel 2 steps again, the ref will arrive at 4. And then the slow will move from 6 to 8, right? Because 2 steps. So here is the slow. And then we travel 2 steps again, so the ref will arrive at here, and the slow will meet at ref with ref. So that's the thing. That's the overall logic. So this is the key caseness. But here, this is very crucial. M minus 1 is not negative, right? So that's why you can always pick 1 length out this m mathematically. But let's analyze example 1 so in order to understand this point. So here k equals 1 in example 1, right? So the cycle length is 3. So n cycle is 3. And then, so let's see the fast, slow, and fast. Slow is 3, and fast is 3 at the very beginning. So now we move 1 step. So we arrive at this 2. 2 is actually the entry point, right? So let's see. Slow equals 2, and fast equals 0, right? They do not meet. And then we do slow equals 0, and fast will be 2, right? From 0 to -4 to 2. This will be 2. And then we move again. So slow will be at -4, and then fast from 2 to -4, and the fast is also -4. This is where they meet. They meet at 4. So in other words, the slow enters the cycle 2 steps. In other words, n slow equals 2. So in this example, the cycle length is 3, right? So n cycle length is 3. So how many steps we have? We traveled. So 1 step, 2 1 step. So here 1 step, 2 step, 3 step, right? So for 3 steps, so the faster pointer moves 6, and the slower pointer moves also 3 in distance. So here 6 is distance, means counting the number of passes. Let's see, the distance between 2 consecutive nodes is 1, right? So this is a 3. 3 is nothing but the length. So here, let me do this. So here, let's see how many steps. So 1 step, 2 step. So 1 step and here, right? 2 step and 0, and third step, 3 steps. So in this one, so let me write like this, right? So here, so we know 2 times k equals 1, because we just need 1 step to arrive at the entry point. So then plus the n slow, so the steps after the slow enters. So this will be, let's see, 2, right? So this will be equal to the k is 1 plus n slow, this is also 2, plus 1 times the cycle length, that is 3. So this is the equality, right? So then I use this, so we can see here, this is right here, let's say 2, this is the k plus in cycle, in slow, right? So this is the k plus in slow plus m times in cycle. But here k is 1, n slow is 2, and m is exactly 1, right? So what we do, actually, we use this 2k, 2 times 1 minus this 1, so we get 1. And then here we have 2 times n slow, here is 1 n slow, so we have negative n slow, that is -2. Then plus 1 times 3, right? So here 1 equals, I borrow 1, 3 from here, so it's 3 minus 2, then plus 1 minus 0 times 3. So this is the rigorous sorting process or reasoning process mathematically. So in this case, because both of them, the slow is pointing -4, then you move, so here is the beginning, so you move 1 step, they will meet, right? But in this, in our example, it moves 6 steps to meet. But during this 6th step, so the slow actually moves 2 cycles, one more cycle around this cycle in the linked list. That's what I want to mention. So overall, so this part, I guess, where m is greater than or equal to 1 is the key, so that you can do this algebra formally, and then you can make the solution rigorous. So now let's look at the the coding part. So the coding actually is rather straightforward. So let's do this. In order to make this more clear, I'm going to write like this: slow point to height, fast also point to height, and reference point to height. So actually we can write like this: slow equals fast equals ref equals height, but it's not very clear from the pedagogical point of view. So okay, so we'll do this slow, fast, and ref. And now what we are going to do, I'm going to use a flag, so false, called found, not found the entry point yet. So I'm going to use false. So I just want to provide one way of writing, but it actually can later shrink or compactify the coding. So basically, let's do a while loop, while fast, and fast next. The reason we do fast and fast next, first, in order to talk about fast next, we need fast to be not now. That's why we have this condition. The reason we want to do this because we want to update the fast as this fast next next. In order to call the second next, we need fast next itself be not now, right? So that's the logic. Then we do this slow equals slow next, fast equals fast next next. So this way, that's the slow and fast meet. So if slow equals fast as a list node, so we are going to set found to be true, and then we can break. So so this basically this is a cycle detecting logic. So after the while loop, if not found, so it means that there's no cycle. We're going to return none, or you can just write not return. So let's return now. Otherwise, so we know, for example, here in this example, slow and fast meet at a certain point. So in this example, slow and fast meet at the 8 here. Then we start moving reference or the height and the slow at the same time, but each time we move both of the two pointers one step forward. So basically the logic is this. Well, ref does not equal to slow. Then we are going to do ref equals ref next, and slow equals slow next. So as we explained, these two must meet. So we just need to return either slow or reference. Let's return reference. So, or you can write reference as a result. So this is the logic. So, but this logic actually contains a lot of backend thoughts under the hood. Now I guess we can do a test. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So actually, if you like, actually you can shrink the code a little bit. Let me briefly comment on that. So I'm going to copy this one. So then I want to change this one to be slow and fast and ref, and comment out this line. And then what I'm going to do, so fast, slow, and fast are the same. So we can bring this part of code here. So just return reference. So we don't need to break because we have already used this one. And afterwards, so if nothing has returned, so we just need to return null, or just a return. Let's write null. So these two actually are same code in logic, but the first one actually I feel it's more friendly to beginners. So I'm going to make this one version v1. Let's check this one, right? Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the cases. So personally, if I wrote this, if I plan to write a solution, maybe I will write like this. So this, like the way we write here, though we use 3 lines, it's more clear. It's clearer, I would say. Here it's a little bit compact, but for readability, maybe the version v1 is better. So here version v2. So if you directly look at the code, maybe need some thoughts to digest. So with that said, I guess that's about it for this specific problem. So thank you.